I'm sorry, Huber. Who? Yes. Okay. So what does this say? For example, here's an example. The square root of 3. Can anyone tell us is 3 to which power?
To the second power.
Careful, yeah. Careful. So these two cannot be the same, right? So these two cannot be the same. 3 squared is 9. Has nothing to do with the square root of 3. So the square root of 3 is the same with 3. Just mimic this. All you have to do is just think in these terms. That's why I put it here, and this is an example for that. So first of all, you have to say that the power is a fraction.
Let me see it.
So it'd be 1/2.
Yes, indeed, it is 1/2, because the 2 here is not written. Is by convention we don't write it. So please remember the square root of 2 is 3. The square root of 3 is 3 to 1/2. 3 squared is 9. They have nothing to do with each other. Perfect. Okay. So I would like now us to pick some problems and practice this, just a few. Rewrite each of the following as an equivalent expression with radical notation. Fine. So from here we are given exponents to change it into radicals. Here we are given radicals to change it into exponents. And here we're asked to simplify. So let's choose one from 45 through 54. Let's say 51. In 51, we have b to negative 1/3. Okay, so what do I do with this first? What is the first step here? What does b to negative 1/3 mean? First of all, I have to use this. So how do I change that? b to negative 1/3. Anyone, please. Anyone?
Would it be 1 over b to the negative 1/3?
So that's okay. That's why we're here. See the difference? Is that clear?
It's b cubed.
So you see that.
B cubed.
So do you see that this is negative and this is positive? That's the first thing. If it's b to 1/3, if it's b to 1/3, it cannot be b cubed. B to a fractional exponent, it has to change into a radical. Not to be cubed. Not b cubed. This is a fractional exponent. So this is 1
and if the
over.
exponent's negative, then that's why it goes in the bottom of the fraction.
No, this was given to us as a fraction, so now it's a fraction here. So this is negative 1/3, this is positive 1/3.
Okay.
And now I have to change this back into a radical. How do I do that? We already had an example with 3 to 1/2. What will this be? What radical is? Yes.
B under the square root.
But
the cubed root.
Yes, indeed, the cube root of b, exactly. Every time I see an exponent that is a fraction, I know this whole thing is a radical. And the denominator is always the index. The numerator is always the power. The numerator is always the power. The denominator is always the index. Good. Let's move on. Other examples? Anything? Let's look at 53. So in 53 we have x squared plus 3. Sorry. Okay, yeah, it's a different exponent. Good. I thought it was the same exponent. Okay. Can anyone tell us how to rewrite this? What is the first step? Anyone, please?
1 over?
Yes, indeed. The first thing is 1 over x squared plus 3 to which power? Awesome.
To the half power?
Yes, 1/2. Awesome. And now final step. What radical is power 1/2?
Is it just the square root of x squared plus 3?
That's it. And please understand this cannot be further simplified. Awesome. Okay, so let's look on this 55 to 64. Rewrite each following as an equivalent expression with fractional or rational exponents. Same thing. Okay, page 4. Let's start with 61. You pick, of course, if you like, page 60. 61. So it's 1 over the square root of t to the 5th. And as you notice, because it's t to the 5th, they're wrong, completely wrong. Okay. I agree with t not equal 0, but if it's because it's a square root, they also have to say greater than 0. Not only not equal to 0. This is an error. Okay. So for the domain of this function, I have to have t greater than 0. Not only not equal to 0, but it has to be positive. Good. So then what do? I want to change 1 over this, or let's change it first in the denominator. Is t to which power?
Negative 1/2.
Careful. The power is 5. The index is 2. Try again.
5/2.
5/2. Now I want to bring it to the top. What should the power be here so that it's 1 over t to 5/2? What should this power be so then the answer
5.
so that the answer is
5.
1, the answer is 1 over t to
Oh.
5/2.
Negative 5.
Yes, not negative 5, but negative 5/2. Indeed, this is it. Perfect. Any questions? Let's also look at 59. 59 has the 4th root of x to the 12th. Now here they are correct. Indeed, x has to be greater than or equal to 0 because the index is 4. I agree with that. So t greater than or equal to 0. Oh, x, of course. Sorry. Good. So can anyone simplify this or tell us how to continue? Anyone, please?
Would it be 1 over x?
So this is the 4th root of x to the 12th. It's not in the denominator. It doesn't have a negative exponent, so I cannot use those properties.
Okay, so would it be x raised to
Yes. Yes,
12/4?
exactly. Done. Very good. Awesome. Don't try to, I'm not saying that that's what, but I'm saying don't try to apply something that is not applicable. Perfect. What about 63? One more. So 1 over the square root of x squared plus 7. Now this is a different story, right? It has like the 61, it has a radical in the denominator. So first I have to change the radical in the denominator and then one more step. How do I change this? Anyone, please? Give it a shot. Give it a shot. Try. Jack, are you with us?
Yep, I'm here. I'm looking at it.
That's okay. Just even if you don't want to try, that's okay too. Anyone, please?
Would be x squared plus 7 to 1/2.
Excellent. Perfect. Now, final step.
Negative 1/2.
More details. I cannot write
X
negative.
squared
I cannot write
7.
negative. It's clear that I cannot write negative 1/2, right?
X squared plus 7 to negative 1/2.
Brilliant. Thank you so much. Awesome. Great job. That's all I needed. Perfect. Okay. Now, also here in the nonlinear models, I just want to present few graphs. So in linear models, we had that line, right? Or horizontal. These are all linear functions. How come that I'm not adding this one? This is not a function. Not a function. So in linear models or linear functions, we can have this function, or this function. But what about nonlinear? There are so many that we need a whole day to talk about them, but just a few of them. Quadratic, absolute value, and rational. Okay, so here's the quadratic. We graphed it some time ago, x squared. Here's the absolute value function. It's a v function. Here's the rational. So this is quadratic. Here is absolute value. And here's rational. Here's the graph of a rational function. Not a friendly function. So what can anyone tell us the domain of this one? Domain of
Negative infinity to infinity.
excellent. Can anyone give us the domain of this one?
Negative infinity to infinity.
Excellent. But this one is not friendly. What will be the domain of this one?
Would it be negative infinity to 0?
Yes.
Union.
Yes.
0 to infinity.
Yes. In plain English, everything but 0. What about the range of this?
Negative infinity to 0.
Exactly the same
Union,
thing.
and then
Yes.
yeah,
Awesome.
yeah.
Brilliant. Thank you so much. Good. So these are major functions. Please remember them because we are going to see them again this class. Okay, what I would like to work on right now is something called demand and supply, an equilibrium point. Demand, supply, equilibrium point. What does that mean? Okay, so let's discuss that, and then we'll look at examples. Demand, supply, demand, supply, and equilibrium point. Okay. So on a coordinate system with number of units and price per unit, we have these two functions, demand and supply. So here's the demand function. It's an example. We're going to look at a few of them in a minute. So why is this a demand? And normally is denoted by D or D of X, demand function. What does this mean? Notice here that the number of units decreases as the price increases. The number of units increases as the price decreases. So we are willing to pay, we're willing to buy more units if the price is low. If the price is very high, we're willing to buy very few units. So it's a decreasing function. Okay, what about the supply function? The supply function is an increasing function, something like this. So S of X supply. Because this is, supply means the manufacturers. What are they willing to supply? They don't want to supply at the very low price. They don't want to supply too many units. But if the price goes higher, they're willing to supply many units. So this is an increasing function. Increasing, and this is decreasing. The equilibrium point is right here when everybody is happy. Number of units and price per unit. At this point, the consumers are happy, the suppliers are happy. With this number of units, so I'm going to say this, let's say A and B. A is the number of units and B is the price per unit. The equilibrium point is a point, EP, equilibrium point, A comma B. We're going to look at a few functions, a few graphs, and determine the equilibrium point. So we have from 77 through 84. So let's choose any of these that you like.